So now that we have learned about how to draw Lewis dot structures, we're going to move on to some of the more nuanced and specific just examples where the rules that we used before aren't going to be enough to give us a good Lewis dot structure. We need to just learn some more advanced aspects to this. And one of them is resonance structures. Resonance structures occur when given the same molecular formula. So one molecular formula, for example, here, we're going to be doing the polyatomic ion nitrate. So given nitrate, NO3 with a 1- charge, we can actually draw 3 different Lewis dot structures based on that. And they would be considered equivalent structures because it's the same number of bonds, it's the same to the same atoms. In AP chemistry, we talk about drawing 2 different Lewis dot structures that would be non-equivalent. And we would have to use a process called formal charge in order to figure out which one is most stable and therefore exists in nature. So resonance is when there are several ways to draw a structure and all of the structures are equivalent. Scientists say that they are resonance structures. One example of this is the nitrate. Each of these structures predict that 2 of the oxygen-nitrogen bonds will be very similar to single bonds, but one bond will have characteristics of a double bond, right? And if you look at the 3 over here, right, you see that when we go ahead and, nitrate would be 5 plus 18 plus 1, right? Because we would have that. So that would be 24 valence electrons. And when we draw it out, right, we would minus 6, and that would give us 18 left over. And so we would be able to put lone pairs on all of the non-central atoms, and then we would be stuck. And when we get to this case, we always say, okay, we need to make a double bond. And the question is, which oxygen do I make a double bond with? So you can see that the 3 possible choices are making the double bond with the top oxygen, the left oxygen, or the right oxygen. But in experiments, we're back here now, in experiments, scientists have shown that the actual structure has 3 identical nitrogen-oxygen bonds. These bonds they're not double bonds, they're not single bonds. They have a length and a strength that would be somewhere in between a single bond and a double bond. And so it's more like in nitrate, it's not the picture on the top or the picture in the middle or the picture down bottom. It's more of an average of the 3. That's sort of key, that it is not one of these. It's never one of these. Some students get a misconception that double bond changes when sometimes it's this with the top oxygen and sometimes it's with the oxygen on the left or the right. And that is not true. It's really like 1 1/3 bond spread out throughout the entire molecule. And that sort of goes against what we have learned as our understanding of how bonds are. What we have thought of is those electrons can either be shared between 2 atoms or they're lone pairs. And this is basically, we're saying that, that is too simple of a model to really explain what is going on in the real world, right? Nitrate does not exist as one of these 3 structures. It exists as an average of these 3 structures, and that's called resonance, right? Resonance occurs when there's more than one valid Lewis dot structure. And the model that we have used before, which is really about localized electrons. Electrons are either lone pairs or they are in bonds. And a bond is when a pair of electrons is shared between just 2 atoms. That model is just not adequate enough to really explain everything that we see in nature. So in nature, the electrons are actually this word called delocalized. We saw delocalized electrons when we looked at the structure of metals, and the electrons in metals were in an electron sea, and we call those delocalized electrons. These electrons are similar, are kind of similar to that because they can move around the whole molecule. So think of the electrons in this double bond not just be, sharing between this nitrogen and this oxygen, but then going between this nitrogen and this oxygen and this nitrogen and this oxygen. So those bonds, or those electrons in that double bond, are sort of spread out between all three atoms, all three oxygen atoms. So it's more like 1 1/3 of a bond. And so there's two different ways that we can write resonance structures. We can either draw all three of them, or sometimes there's just two of them. But we can either draw all the resonance structures and draw these like double-headed arrows in between them, showing that it's not that one of these is the structure of nitrate, but it's the average of all the three. This is the way that the College Board prefers you to write this in like on the AP test. In organic chemistry, and this is the way that I prefer it, instead of showing all three possible structures that it's the average of, I like this idea of writing a solid line and a dashed line to represent not a single bond, not a double bond, but something in between. That helps us to understand that it isn't one of those three, that it's the average of them. The problem with that is that you're never going to be able to correctly or accurately draw the lone pairs on the outside atoms with that. You can see if you were to count up the electrons in this, it doesn't actually sort of work. And so what I do is I just leave those electrons off. As we will see, when we're going forward and we're looking at shape and polarity and intermolecular forces, all the things that we derive from the Lewis dot structure, that the electrons on the outside atoms are really inconsequential. So here's two more examples of resonance. The first example here is the nitrite polyatomic ion, right? Nitrogen has 5 valence electrons, 2 oxygens would bring 12, and we would have 1 because of the negative sign. So it would have a total of 18 valence electrons. Nitrogen would of course be in the middle. The oxygens would be on the outside. I used 4, that gives me 14 left over. Now I draw in the lone pairs on the outside atoms, right? I fill the outside first and then I fill the inside. Now I'm at that place where I would need to make a double bond. And of course, which oxygen? I only need to make one double bond. This isn't like CO2. I only need to make one double bond. And what do I make it between? Do I make it between the oxygen on the left or the oxygen on the right? And the way that I prefer to write this is that I choose neither the oxygen on the left or the oxygen on the right. It makes a bond and a half with the 2 oxygens. This is just another way of saying a double bond on one side and a single bond on the other side. And when you do it that way, you are able to accurately write in the electrons on the outside, right? The oxygen could be double bonded on the other side as well. So we have 2 different ways of drawing resonance structures. This would be the resonance hybrid model, sometimes that is called, and these might be called resonance structures, meaning plural. And either one of these is going to be acceptable on the test. Like I said, the one in yellow is my preferred way of drawing it because I think the way in pink, it gives students a misconception that it flips between those two Lewis dot structures, when in actuality, it doesn't flip between those at all. It just is the average of the 2. I feel like it's, instead of saying green paint, it's like saying this is the mixture of yellow and blue paint. Like, well, why don't you just show the green paint? Give the oxygen atom, give the oxygen molecule this isn't the oxygen molecule. Give the ozone molecule here a try. to see if you can predict whether this molecule will need resonance. And then if you decide it does need resonance, what would be the resonance, either hybrid structure or the two resonance structures that it is an average of. So pause the video, try to do O3, ozone, and then restart the video and see how you did. So you can see here that these two molecules have the exact same structure. They're made of 3 atoms and the total number of valence electrons is 18. So it actually doesn't matter that nitrite has 1 nitrogen and 2 oxygen, where ozone has 3 oxygen. They actually wind up being the exact same structure, where there's a central oxygen in the middle and for ozone, and you can either have the double bond with 1 oxygen on the left or the 1 oxygen on the right. It would be the average of those two, and as shown in pink, or the resonance hybrid structure with the dashed lines representing 1.5 bonds shown in yellow.